The next big area we're going to study involves units of measurement. And before I start on this, I just want to emphasize that although the ability to convert units is a skill that we will certainly use in Chemistry 130, it's not so much unit conversions themselves that are really the important subject that we're learning here, but rather the technique of dimensional analysis, which we will employ later on in our study of stoichiometry and manipulation of solution concentrations in a number of other ways. So it's really the technique of solving problems which ought to be the focus for us here. Now, as we know, there are units associated with most of the measurements that we're going to deal with. So, for example, when we're talking about lengths, we have inches, we of course have centimeters, miles, a whole range of them. We have units of time. We can have composite units, like for example speed, which combines both length and time, so that is a length per unit time. And we do run into values that we are going to use which are, for convenience, often going to be unitless. Although we won't really see much of those this semester. Next semester you'll study acids and bases, and you'll talk about pH, where we do run into a unitless value, and equilibrium constants, which are typically presented as unitless. We have a couple different systems of units, and we're going to largely use the SI system in this class, although the United States customary unit systems, which include inches and feet, will of course come up in this class as well. So table 1.1 of the textbook gives you a list of the fundamental SI units. You'll notice that with the exception of the kilogram here, all of these are what I would call just simple base units, so one word things, meter, second, Kelvin, etc. The kilogram is essentially defined more for convenience of physicists with the kilo already there, but I would generally consider the base unit of mass to be the gram. You have milligrams, centigrams, etc. They're all based on the gram. It's just that, as I said, the kilogram is defined more for convenience when we deal with physics. In table 1.2 of the textbook, we also encounter several prefixes, and these should already be largely familiar to you. And these prefixes essentially indicate what multiple of 10 we are referring to in reference to a unit. So, for example, when we talk about centimeters, centi is equivalent to the decimal notation 0.01, or the exponential notation 10 to the minus 2, or very importantly in words, centi is 100th, and milli, with a lowercase m, is 0.001, which would be thousandths, etc. As far as these values go, I want you to know all of the prefixes that appear in blue on this table, although tera and giga are probably not quite as important in chemistry. And when I say know, what I want you to do is be able to know the full prefix, know the symbol, know the meaning and exponential notation, and to the best of your ability, be able to do it in words. That should be easy for some of these, but maybe a little trickier for others. For example, milli is 1,000th. What is micro? Micro is a millionth, and a nano would be a billionth. That might not be immediately apparent, but with practice, you'll get to know that. Now, in this class, we're going to deal with units with a little bit more sophistication than we did in an introductory chemistry class. I want you to always think of units essentially as multipliers, just like you would, for example, think of variables in algebra, like x or what have you. So, for example, the prefix is a power of 10, as we said, but the prefix kilo, or abbreviated as a lowercase k, is just exactly the same as a number 1,000, or 10 to the 3. So when we look at 1 km, 1 kilometer, you always want to be able to see that as being like a multiplication problem of 1 times the K, which stands for 1,000, times meters. So 1 times 1,000 meters, or 1,000 meters. And the same thing with the example right below that, 4.5 kilometers. The K stands for 1,000, so it's just 4.5 times 1,000 meters, or 4,500 meters. On the right, we have examples using milli, which stands for thousands. So 1 milliliter is 1,000th of a liter. And I think if you can think of the prefixes standing in that way, it will always keep you correct and prevent you from getting the prefixes and their meanings backwards, which is a common problem when we're dealing with the metric system. Okay, so ultimately, the way I usually like to teach this when I'm first presenting it to students is to say we always want to put a 1 in front of the unit with the prefix. So in this particular case here, we have 1 kilometer. So the unit with the prefix, the K, has a 1 in front of it. And then you simply replace the prefix with its meaning on the other side of the equation. So 1 kilometer is the same thing as 10 to the 3 meters, 10 to the third, or 1,000 meters. 1 microliter, using the Greek letter mu there, we can replace the mu with its meaning, 10 to the negative 6, so that's 10 to the minus 6 liters, or a millionth of a liter. Now, what we can always do is divide both sides by the non-1 value on either side. So, for example, if we look at the first equation here, 1 kilometer, 10 to the third. We divide both sides of the equation by 10 to the third. And you'll notice that simply changes 10 to the third to its inverse. We put it on the opposite side. So 10 to the negative 3 kilometers is 1 meter. So if we want to write it with a 1 on the opposite side, 1 not in front of the prefix, but 1 in front of the base unit, we simply put the reciprocal of the power of 10. So kilo's reciprocal, kilo is 10 to the positive 3, so you put 10 to the negative 3 in front of it. Microliter, well, micro is 10 to the minus 6, so its reciprocal goes in front, 10 to the positive 6. And, of course, 10 to the positive 6 times 10 to the negative 6, we add the exponents. 6 plus negative 6 is 10 to the 0, which is 1. All right, so let's go ahead and write that out to make sure that it's essentially clear here. So what I just said a second ago, 10 to the minus 3 kilometers. Well, we can substitute in positive 3 there. So 10 to the negative 3 times 10 to the positive 3 meters is the same as 10 to the negative 3 plus 3, because when we multiply numbers, same number to different powers, we just add them, which is the same as 10 to the 0, which is, of course, 1. So that's why we say 10 to the minus 3 kilometers is 1 meter. And now it should follow that if we go ahead and say, well, 10 to the minus 3 kilometers is 1 meter, and 1 meter is also, say, 10 to the second centimeters, or 10 to the sixth microliters, we could make these two equivalent. They're both equal to 1 meter. So that can shorten our conversions a little bit later on. So why is that? Well, because again, this whole thing, 10 to the negative third kilo is 1. 10 to the squared second centi is 1. So they're both 1 meter equals 1 meter. It's the same thing. Now, the risk inherent in doing conversions this way is that if you're not very careful with what you're doing, you could get these backwards. So let's ask ourselves, is the next statement true here? 10 to the negative 2 centimeters, is that equal to 10 to the negative third millimeters? Well, no. 10 to the minus 2 centimeters, centi is 10 to the minus 2. So 10 to the minus 2 times centi stands in for 10 to the minus 2, meters. Does that equal, well, milli is 10 to the minus 3. So 10 to the minus 3 times 10 to the minus 3 meters. 10 to the negative 2 times 10 to the negative 2 is 10 to the negative 4 meters. 10 to the negative 3 times 10 to the negative 3 is 10 to the negative 6. We add them. Are these equal? Absolutely not. No. These are not equal. Now, if you're not comfortable using this kind of shortcut method here, feel free, of course, to do it the way that I teach in 120 that always works, which is to say, we put a 1 in front of the unit with the prefix and the meaning of the prefix on the opposite side, and that will always work for you. Okay. In the next video, we'll go ahead and look at dimensional analysis. Thank you.